I know. I don't know. I did that.
All right, ladies and gentlemen.
I did the work.
I have to be very professional right now because I'm recording this lecture for the people that are not here.
So you should answer Dimitri's questions.
That's right. That's right.
Can we also say
do
hi
that
to
before?
Dimitri?
Okay. So yesterday, what did we talk about?
We talked about the types of radioactivity.
Nice. Refresh my memory. Alpha particles.
When a helium nuclei,
Yeah.
something, and it ionizes.
Yes. It ionizes particles. What do you mean by ionized particles, Mel?
Yeah, that was a hard word.
Well, what's an ion? From grade 9 science. Any charged particle, right? So if I ionize a neutral particle, what am I doing?
You're adding electrons. Or you're adding
Yeah, or even a proton if we have high enough.
You said protons don't leave because
They can be. If it's a high enough energy particle smashing into a nucleus, it cannot go to proton. Which is even worse. I don't have the specific energy amount. It's in like it has to be really high.
Will water transfer some gold?
Any of the three, any of the three, if they're high enough energy, can knock out a proton. Yeah, but mostly we'll talk about ionization, knocking electrons out of orbit. Okay. First thing we're going to talk about today, Sanger plots. It's a cool name. I like it. You think of when you do grade 9 and grade 10 chemistry, you kind of talk about neutrons and protons being roughly the same number. Kind of talk about because you only deal with the first few elements in the periodic table. You talk about helium, 2 protons, 2 neutrons. Lithium, you might talk about 3 protons, 3 or 4 neutrons. But as we're going to see, as we get farther away from, as we get to a higher number of protons, the ratio of neutrons to protons goes up, right? And this is the line that represents the 1-to-1 neutron to proton ratio. And as you can see, sure, down in the first few elements it's about equal, but then it starts to veer up.
It's like an exponential.
That's right. And the reason for that, let's just fill in this blank here. So this is a graph of the elements. A Sanger plot is a graph of the elements which portrays the range of stable and unstable isotopes. First blank fill in, what's an unstable isotope called?
Radioactive.
Take it radio and then isotope. So it's
Radio.
it's radioisotope.
Radio show.
I like it, radio show.
Radio show.
For each atomic number. Let's make sure I'm recording here. The graph on the right of this page primarily displays the stable isotopes. So this one displays stable isotopes only. It's got this band of, that band of like light salmon color is the realm in which stable isotopes exist. So for any, let's take a look at atomic number, let's pick atomic number 50. If we go up here to atomic number 50, we've got one unstable isotope, but then every single other isotope up in this realm is stable. Okay, so we can have, it looks like 63, 64, 65, 67, 68, 69, 70, 71, or 73 neutrons to balance out those 50 protons.
What's 20? We got 20?
Yeah, what about 20?
What is that?
I don't have a periodic table.
Can we get one?
Yeah, okay. Give me a second.
Wait, just wait. Check your number 4 second.
No,
nitrogen. I haven't
What is
master.
No, it's not nitrogen. It's sodium.
Really? Which one are you looking for?
Sodium 21.
Which one are you looking for?
Then it's fluorine or argon.
20 is calcium. And 50, what I was looking at, is tin.
So those are, what does that mean? That they're unstable? Like, what does that mean?
That calcium is 2 unstable isotopes.
It means that calcium
Comes in 2 forms?
No. Shh. So these are all the naturally occurring isotopes. It means that it's got all the isotopes that are in this section are stable, but then these two for calcium, this isotope down here and this isotope up here are unstable.
So they would give off the particles.
Or beta, or we're going to see there's 5 different types
Oh, I
of
get it.
So
radioactive
can we
decay.
get boys pink from drinking radiation things?
But you know, if you look at more specifically, they'll say that like less than
Rare.
0.001% of naturally occurring calcium is going to be radioactive. Okay, so it wouldn't go drinking soy milk right away. Even though it's good for you. Okay, couple notes. Protons and neutrons do not exist in a 1-to-1 ratio, as you would have guessed by looking at the first couple rows of the periodic table. Again, the farther we go up in terms of proton number, the more neutrons it takes to counteract the electromagnetic repulsion. So they have to be spaced farther out. Those little protons have to be spaced farther out in the nucleus because there's so much electromagnetic repulsion from the positive charges.
What about the ratio to gluons?
The ratio of what?
To gluons.
No one knows
Those
that.
we're not even going to talk about those because they're just what make up the subatomic
So there's
particles.
probably so many more.
Well, yeah, there's 3 times every neutron or proton is made up of 3 gluons. Oh, not gluons. Sorry, quarks. Gluons
Maybe even
are the
more.
force-carrying particles for the strong nuclear force.
Exactly. So there should be a ratio.
Yes. See, the problem is the strong nuclear force. When we deal with big atoms, the strong nuclear force. I guess I should draw this. We have huge atoms. The strong nuclear force actually, let's say this is a proton. The strong nuclear force drops off within the range of the atomic nuclei. Okay, there's such a small range for strong nuclear force, it's really effective in small nuclei, but it's less effective in big nuclei. So what happens is you get an overpowering, that's a terrible diagram, but you get an overpowering amount of electromagnetic repulsion from the protons that can't be counteracted by the gluons or the strong nuclear force holding them together. Okay, so you need more neutrons to force the protons apart from each other. Okay, so you take the same amount of protons, but you have to put them farther apart in order to create a stable nucleus. Okay. Larger elements require, this is exactly what it says here. Larger elements require a greater number of neutrons to diminish the electromagnetic repulsion exerted by many protons in a small space. As can be seen in the third graph. Okay, so let's look at next page. These are more complicated Sanger plots. Now yours didn't come out nicely color-coded.
Whoa.
Now these 2 plots are inverse, okay? This I couldn't find. This one has neutrons on the y-axis, protons on the x-axis. The next 2 just flip them, but it's the same plot, so it just curves the other way. So the blue and the purple and the gray way up here, those are naturally occurring isotopes.
Shoot.
Everything else are isotopes, but isotopes that we forced to exist in a lab, or in a nuclear reaction, or in a particle accelerator.
Okay, so this is only talking about radio.
No.
No, it's
So look,
everything.
this band in here, so the band of blue
Yeah.
and purple, that is what's shown in this first one.
Oh.
Okay?
So you don't even show all the others.
These are only natural.
Okay, okay.
Yeah, these are only natural isotopes. Okay? And these ones are all isotopes.
So what do we have to do with these? Like, do they just give us like a chart and we have to?
You just have to, we're going to understand what, we're going to get in more depth here when I go down to the next one. Yeah, so this one just shows stable versus unstable and man-made. The yellow ones are all man-made ones. And then if we go down here,
Are the man-made ones stable or unstable? Or both?
unstable, I believe.
It doesn't say.
Radioactive.
Yeah, man-made radioactive
Oh.
isotopes. Okay?
I think all man-made
So why would you want radioactive?
Yeah, because if they're stable, they exist in nature.
Right.
So the only man-made ones would be unstable.
Oh,
And they
I see.
want that because it would be helpful
Just for science. A lot of them.
How much
people-
money they spend? Just
and-
like-
Yeah, a lot of them just for fun,
burning,
trying to.
burning people inside out. Yeah.
No, just
Yeah, basically.
scientists want to know. They want to know about these unstable radioisotopes. They want to know like how long they last for, if there's any anomalies.
If they can force them to
Going up in the rankings, it says that there are some temporary isotopes or something, the dark.
Short-lived and long-lived. Well, I don't know what they cut off between short-lived and long-lived, but short-lived natural radioisotopes might form in natural radioactive decay, but maybe for only a few milliseconds,
Oh, okay.
and then they decay further. Okay. They're like, you know when you do chemistry, you do Hess's law, where you do all the like a series of chain
Yeah.
reactions, but the intermediary reactions might only be like a few milliseconds to actually go through. It's the same thing for these short-lived radioisotopes. They might exist as an intermediary step, but very quickly. And they
But
break
then
down.
how do you prove that they exist?
Because they actually can catch them breaking down in a lab setting. All right.
This one's a little better.
The third plot is exactly the same as this plot, but it shows specifically what type of decay happens. Now, this is important, okay? So,
Hmm.
if we have too many, sorry, I'm trying to think here. If we have too many neutrons, remember that if we have too many neutrons, that means it changes neutrons to protons and releases an electron. That's that beta decay.
Why don't we have gamma?
Okay. If
Yeah.
we have too few electrons or too few neutrons, then we change protons to neutrons, and that's a different type of decay. Now, the alpha decay is also when you have too few neutrons, but it's in the larger.
Realm.
It's in the realm of larger ones. So, for smaller elements, when we have too few neutrons, it emits what we call beta positive decay or positron decay, which we're going to see in a second here. We're going to get into it. But the alpha decay that we saw yesterday is only for larger unstable elements.
What's the difference between the pink on the top and pink on the bottom?
Oh, the pink on the top is proton decay,
Which,
no.
no,
Which is very, 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 very rare.
and then
that's
all the
ins-
pink on the bottom.
What's that?
The pink on the bottom. It's just
Beta.
That's beta decay.
so that can happen.
That can happen.
a
Yeah.
lot.
Yeah. And same with positron decay or electron capture. And then we get
And
into the
gamma.
realm of
Oh, no, that's alpha.
alpha. Up here is alpha.
Why no gamma?
And I
I think it
actually,
means P.
I
on
don't
photon.
even know what SF means. The green one's way up there.
The purple neutron decay.
No, the purple. Yeah.
Purple is neutron, yeah, neutron decay.
But then I think the P means like photon decay.
Yeah, no, it means proton decay. Gamma, where's gamma?
It doesn't have it. That's why I thought.
Oh,
photon.
yeah, sorry, it doesn't say gamma because gamma is not a, it doesn't change the,
It just changes the.
yeah, it just changes the electron states. It doesn't change the nucleus at all.
So we have to be able to like interpolate these graphs.